going to learn about the matter wave. These are the various points which we include in this lecture. The first one is introduction of the matter wave. Next, characteristic of matter waves. Wave particle duality of light, wave particle duality of matter, and evidences of wave nature and particle nature. Now we have to introducing here about the matter wave. In quantum theory of radiation, matter and wave are the two different terms have different nature. Particle can be specified by its mass, velocity, momentum, and energy. On the other hand, wave is a spread or disturbance in a medium which is specified by its frequency, wavelength, phase, amplitude, and intensity. As two or more waves can occupy at same position at the same time, but for two material particles it is difficult. There will be difference in their positions when they are closer at an instant. But it is interesting to know about the radiation exhibit dual nature. Sometimes it acts as a wave and sometimes it acts as a particle. The phenomenon such as diffraction, interference, and polarization can be explained on the basis of wave nature of the radiation, while the phenomenon like photoelectric effect, blackbody radiation, Compton effect, atomic spectra can be explained on the basis of particle nature of the radiation. In quantum theory, these particles are called as quanta or photon. As radiation has dual nature, the moving material particle also have dual nature, that is particle and wave. It led to the idea of matter wave. This concept of the matter wave was given by scientist Louis de Broglie. Matter wave concept of the de Broglie hypothesis give a birth of quantum mechanics, and therefore de Broglie was honored by Nobel Prize in 1929. The concept of the matter wave helps to develop the theory of radiation in terms of quanta or photon. Here we have to just see the figure, the particle, and if the particle moves, it satisfies a wave. De Broglie proposed that the matter wave hypothesis, a moving material particles are associated with wave, which is called as matter wave. The wave nature of particles like electron that was experimentally confirmed by Davison and Germer, and in the same year by G.P. Thomson, and it leads to uncertainty principle. That uncertainty principle is one of the postulates of the quantum mechanics, which is based on the de Broglie hypothesis. We have to discuss in detail in the next lecture. The concept of matter wave helps to develop the theory of radiation in terms of quanta or the photon. Now we have to see what are the characteristics of the matter wave. Here the first characteristic we will give as lighter the particle, greater is the de Broglie wavelength. That here these terms we have to discuss using the earlier relation. The wavelength of the matter wave, lambda is equal to h by mv, where h is the Planck's constant, m is the mass of the moving particle, and v is the velocity. Now see here, as the particle is lighter, greater is the wavelength of the de Broglie wavelength. Faster the particle moves, smaller is its de Broglie wavelength. De Broglie wavelength of the particle is independent on the charge or nature of the particle. The matter waves are not electromagnetic in nature. Means the matter wave is not just like the progressive wave. It can extend from minus infinity to plus infinity. Matter waves represent the probability of finding the particle in a given Higgs space. Means all the matter waves which are represented by this is matter wave, that concept is totally different in comparison with the progressive wave, or we say water waves or the sound wave. That here this matter wave, it represents the probability that how the particle we have to find at particular point in the given Higgs space. Matter waves are packed over the small region called as wave packet. That wave packet moves along with the particle, and that is shown here. It cannot be emitted or travel in the free space like the radiation. Now we discuss in detail about the wave-particle duality. Our nature manifests in the two fundamental forms like radiation and matter. Radiation, that means the electromagnetic waves of different frequency, the term we call the radiation. That radiation has dual nature, means in some cases it acts as a particle nature and in some cases it acts as a wave nature. In the same manner, the matter also possesses dual nature. Here we discuss dual nature of the light, electromagnetic radiation or the electromagnetic light. Light behaves as a wave. We know that the behavior of here this light, that is explained by the wave theory of the radiation. For example, the interference, diffraction, polarization. These phenomena are the result of the interaction of the light with light. From the experimental observation, it is concluded that the light is a transverse wave motion. Therefore, they are explained by the wave theory and electromagnetic radiation. Similarly, how the light behaves as the particle. Light behaves as particle. That term we have to explain by the various phenomena such as blackbody radiation, photoelectric effect, Compton effect, which were produced by the interaction of the radiation with matter and cannot be explained by the wave theory. To explain these phenomena, radiant energy is considered as a stream of small packet of the energy. That packet of the energy we call as a light quanta or photon. The energy released, energy assigned to each photon is of the order of h nu. Therefore, that relation you know, E is equal to h nu. Now we see what is the relation between particle and wave properties of the light. Here we have to say the duality of the matter wave or the radiation. That means the lattice particle parameter and wave parameter we just take into consideration. Here the energy and the frequency which are related by the relation E is equal to h nu, where h is the Planck constant, nu is the frequency of the radiation. The particle parameters are energy and momentum, while the wave parameters are frequency and wave vector k, or you say the 2 pi by lambda. Also, we have to find the relation between momentum and the wavelength. For that purpose, we use the relativistic formula related to the energy and the momentum. That relation is E square is equal to P square C square plus M square C raised to 4. Here, if the particle is moving with velocity comparable to the velocity of the light, its rest mass is 0. Therefore, the second term in that equation becomes 0 and we get E square is equal to P square C square. Therefore, we write the relation E equal to PC, and we know the wavelength and the frequency related by a term C is equal to lambda nu, or lambda is equal to C by nu. Simplifying these two terms, we separate the P equal to h by the lambda. From the earlier equation, lambda is equal to h by P. Therefore, P is equal to h by lambda. That is equal to h nu divided by C. We have to put the value of the lambda. Lambda is equal to C by nu. Therefore, we get the P is equal to h nu divided by C. That h nu divided by C, we have to simplifying the term h divided here by h nu divided by C in terms of the wave vector k. How you find that relation? H divided by the 2 pi, and the other term we write k equal to 2 pi by lambda, and therefore you get the term E equal to h cross omega. How we get the E equal to h cross omega? That E equal to h nu, that term is simplified. H divided by 2 pi means we have to multiply to the numerator and denominator by 2 pi. The equation becomes h divided by 2 pi into 2 pi nu. H by 2 pi is the h cross and 2 pi nu is the angular frequency omega. And how you get the P equal to h cross k? The same early relation, P equal to h by lambda multiply to the numerator and denominator by 2 pi. Therefore, we get the h divided by 2 pi into 2 pi by lambda. This 2 pi by lambda is the k, and h divided by 2 pi, that is the h cross. Sometimes we call this h bar. This is the reduced Planck constant. Hence, E equal to h cross omega and P equal to h cross k. These two terms indicate this particle parameter are related to wave parameter, and these wave parameters are related to particle parameter, and therefore the radiation which exhibit the dual nature. Now, dual nature of the matter. We have discussed earlier the matter which composed of number of particles like electron, neutron, proton, and as the particles moves, waves are associated, that we call the matter wave. Such a matter wave also has duality. In some cases, it acts as a particle nature. In some cases, it acts as a wave nature. That concept was given by Louis de Broglie in 1924 and proved that moving matter is associated with a wave that is called the matter wave. Such a matter has wave particle duality whose wavelength equal to lambda is equal to h divided by mv or h divided by p, where h is the Planck constant. That constant is 6 into 10 raised to minus 34 joule second, and mass of the material particle, and v is its velocity. Such a matter has wave nature that was verified experimentally by Davison and Germer in 1927. Now here are some evidences to show the wave nature of light. That here this figure shows this light, the plane wavefront, which is incident on a slit, two slits. Plane wavefront, how we get? If the light is coming from infinite distance, it becomes the plane wavefront. Now, once it diffract through the two slits, these the spherical wavefronts are superimposed and we get the interference here, the pattern. That interference patterns, which consist of alternately dark and bright bands. These dark bands, these are the result of the destructive interference. Bright bands which are due to the constructive interference. Next evidence is for black body radiation, and that here the black body radiation is a result of the particle behavior of the light. When the black bodies are heated, only specific color of the lights are emitted. That is, at particular temperature, that is 1000 Kelvin, the black body emits a soft red glow. That is this radiation, and it has particle behavior. Similarly, as the temperature increases, the radiation becomes brighter and more orange color. Again, temperature increase of near about the 2000 K, it becomes more brighter and here the white in color. That concept was given by Max Planck in 1900, and he proposed that the light is emitted in the form of shower of particles. Means this black body radiation, that here this phenomena which is explained by using the particle nature of the light. Here the particles only absorb or it gives off the specific packet or the quanta of the light energy. These packet of energies are called as photon. Each photon has its own energy and frequency nu. Therefore, energy of the photon E equal to h nu. Next effect is the photoelectric effect. It also based on the particle behavior of the light. That evidence was given by explained by the Einstein. Einstein used the particle nature of the light and explained the theory of the photoelectric effect. And for that this work he got a Nobel Prize in 1921. The results in that this experiment, which are exactly same, theoretical and experimental results are to be same here. Here is one, here this figure, it show how the photoelectric effect which show the particle behavior of the light. Here it show a evacuated here this chamber. In that is the cathode and anode. When the light is focused on that here this cathode, the electrons are ejected. These electrons are attracted on this plate, and here this meter show the electron here the flow here. This is the result of when the light is incident on the cathode, it emits the electrons. That electrons behaves as a particle nature. Such a here is concept which is used today in electric eye security devices as well as automatic door opening etc. Thank you. We will see in the next lecture in the next article. Okay, bye.